So this big awful example that we worked out with P2 and this map from P2 to R2, if you sort of take a step back and describe what happened in general, this is what happened. Okay, so there's two pieces we have to describe. There is how we started with a map and came up with a matrix, and then how we interpreted the matrix being a linear map from R3 to R2. So here's how it worked in general, right? So we had a vector space, V, with a basis, some basis elements B1 to Bn. We had a codomain space, W, with its own basis, gamma 1 through gamma m. And we have a linear map, H, going from V to W. So to get our matrix, we took each basis element from the basis for V, hit it with H. That produces an element of W. We write that element in terms of the basis that we have for W. Right? That gives us this. Then we pick off these coordinates, or these coefficients, and that gives us a column of entries. Then we do the same thing for every other basis element down to the last basis element for V. We hit it with H, write the result as a linear combination of the basis elements for W, and then these coefficients give us a column. Finally, to get the matrix, we take all of these columns and shove them all together into one big matrix. This matrix is what we will call the representation of the linear map H with respect to the basis B and D. So it turns out the entries that you get here depend not only on what the linear map is, but also what bases you chose to begin with. So we have to kind of decorate this with not just H, but also B and D, so that they all kind of show up since they all affect the result. But just as a reminder, what this matrix is telling you, right? Each column corresponds to a basis element for V. So this is the beta 1 column. And each row corresponds to a basis element for W. So this is the gamma 1 column down to the gamma m column. And what these entries tell you is they tell you what coefficient you need on the gammas to produce f of beta 1, or sorry, h of beta 1. So by reading this column, we know that h of beta 1 is, right, h11 times the basis element corresponding to that row, which is gamma 1, plus, and so on, down to the last one, hm1 times the basis element corresponding to the last row, which is gamma m. And sure enough, right, this is right because look, this is what we said to begin with. Okay, so this is how you get this matrix. Right? Write each for your basis for V. Hit each basis element with your linear map. Write the results in terms of your basis for W. Pull off those coefficients as columns. Put all the columns together into a matrix. And this is the matrix that represents this linear map. Now we have to say, what do we mean by this matrix representing the linear map? We will mean exactly the same thing as we did in the example. So because, so we've chosen this basis B for V, and that gives us the representation map to Rn. Right? H is here, W is there, rep D takes us to Rm, and this matrix, which maybe we should call capital H, or we're calling it rep BD of H. Okay, so this matrix is supposed to be transporting us from Rn to Rm in a way that sort of makes this round trip the same as that trip, right? So we have to say, how does this matrix act on Rn? How does it sort of behave as a linear map? And it will be exactly the same as in the example. So if we have a matrix that is m by n, that's this matrix, and a vector that is n by 1, that's this vector, we will, just like in the example, we will sort of turn the vector sideways like this, and then slide it down, and every time we hit a new row, we multiply and add. So A11 times C1 plus A12 times C2 all the way up to A1n times Cn, so that's the first row. And then we go down to the next row, and so on down to the last row where we get AM1 times C1, that's right here, plus AM2 times C2, and so on up to AMN times Cn, and that's this last one. Okay. So one thing that we haven't proved is that this actually is a linear map from Rn to Rm. It is. We'll prove that later. Notice also that this sort of product operation, you might call it the matrix vector product, I guess. This product operation is only defined when the number of columns of your matrix and the number of rows of your vector are the same, right? Because for this to make sense, when we turn this vector sideways on top of the matrix, it has to sort of have one entry per column in the matrix. Something else you might notice about this operation is that this is actually C1 times A11 down to AM1 plus C2 times A21 down to A12 down to AM2, and so on down to Cn times the vector A1n down to AMN. So what this crazy vector matrix product thing is actually doing is just using the entries from this vector as coefficients on the columns of the matrix to do a linear combination. So that's really what's happening here. Now we've cooked up this definition exactly so that if you start at V and you do H and then rep D, you get the same thing as if you do rep B and then do this matrix product with the matrix that represents H. And this works out exactly like it did in our example, so I won't write out a long-winded proof. It's exactly the same calculation.